This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, next up we have Max West, and he's going to tell us about adversarial robustness and guarantees for quantum classifiers.
Okay, thanks Josh. Yeah, so I'm going to talk about this kind of weird problem of adversarial vulnerability in classical and quantum machine learning models. And then we'll see some little bits of numerical evidence of our little quantum classifiers actually not being quite as bad as you might think. And then we'll see a few things that we can say analytically about what's going on. All right, so adversarial vulnerability is this sort of kind of wild phenomenon where even these sort of really powerful, sophisticated classical neural networks that can do all sorts of cool stuff are actually shockingly vulnerable to tiny little perturbations of their input data. So this is a kind of famous example of a model that is doing sort of recognizing semantically similar regions in images. So it sees all the people, they're in different places, but they're all people, which is different to the road, which is different to the buildings in the background. But then if you give it this little guy in the bottom left, which is almost the same as the top left image, but just sort of tampered with just fairly slightly, right? Then the bottom right is what it outputs, which is kind of disturbing, right? If you think about this in a self-driving car or whatever. But this is a kind of a really widespread phenomenon that just happens in these big machine learning models. So in the quantum case, we can actually sort of understand intuitively why something like this might be happening, just as a sort of an artifact of this sort of standard measure concentration phenomena, which I think probably is fairly familiar to most people here. But this is just a sort of prototypical example where I'm sampling points uniformly randomly from spheres, unit spheres in R3, R10, R1024. And you see that they kind of just concentrate really strongly around the equator. And more generally, you can think of this concentration as occurring, for example, around the decision boundaries of classifiers. And then we sort of believe maybe that sort of just a very small perturbation is going to be enough to push you over a decision boundary, which is where the vulnerability is coming from. All right. So this is kind of explaining the existence of adversarial examples, which is not necessarily the same thing as being able to find them. And so typically what you would do is just sort of do some sort of numerical gradient descent procedure that's kind of actually the exact opposite of the training process. So in training, you're optimizing the parameters of a model to minimize the loss function over some input data. But here it's more the model is fixed and you're optimizing the input data to maximize the loss, which is kind of amusing somehow. But so this is not necessarily a realistic threat model if you're trying to actually attack someone's network, right? Where you don't necessarily have the sort of intimate access to it to allow you to do this sort of extended gradient-based attacks. The cool hack that somehow works is that if you just sort of make a network of your own and attack that, and just take the perturbations that generates and submit it to the target network, this sort of also just kind of works. And so the intuition for this is that even sort of very different, very independent classical networks kind of tend to just independently discover sort of similar ways of doing classification. So the little tricks that the adversarial examples that target your network, they're sort of exploiting features that are also present in other classical networks. So by sort of tricking your network, you kind of trick all the other ones just basically for free. So this is an example of this in this sort of easy little data set where we carry out these sort of gradient-based attacks on just a CNN, so in blue. And so here we're explicitly constructing these tiny little perturbations by a gradient-based attack on the convolutional neural network. And then we see that if we just literally take these perturbations and submit them to a ResNet, so this is an entirely different model, with, sort of different architectures trained on different samples, its accuracy drops off sort of almost as quickly. And so the intuition is that the CNN and the ResNet, they're different, but they're sort of secretly basically doing the same sort of thing. And so the crazy little sort of artifacts that the adversarial examples that target the CNN, sort of also present in the ResNet, and so you just sort of trick it sort of straight away. And then when we do the same thing and pass them off to our little quantum classifiers, we sort of see, yeah, the accuracy really not going down anywhere near as quickly. All right, so to be honest, I get a little nervous maybe about reading too much into this specific result, but kind of the high-level intuition is that maybe, okay, so like, as we've heard, like there's really probably not a strong justification for imagining that these quantum computers can do sort of machine learning sort of better than the classical networks. It's sort of like not clear why that would be true, but it is maybe plausible that whatever they do, it's sort of just different, right? It's sort of generically, classically intractable, and so the little artifacts that are all tripping up the classical networks are not necessarily the same as artifacts that would trick a quantum network, because they're just kind of doing different things. All right, so maybe stepping back a little bit and looking just at the general setup. So we mainly consider these sort of like very standard sort of setups where we have like some data, we encode it into like some quantum state, hit it with a parameterized unitary, and then just like measure something, right? So like Z on like the first k qubits. And then if we just consider a sort of binary classification case, where we just take the sign of that expectation value as the prediction, then we can ask, like, how much do you have to change the input data to sort of change the actual prediction of the model? So we want the expectation value to change by at least as much as the magnitude of the initial expectation value. Well, actually, and you want to change it like in the right direction as well, but okay, definitely it's necessary that the change needs to be at least that big. And so typically, well, I forgot to write it. Anyway, typically, your problem is that the initial magnitude of y theta is really small, right? Because everything is sort of concentrating. But if you imagine the sort of very small subspace, subset of states that you actually care about, then you can imagine these being the ones that, if the classifier is well trained, those expectation values have been sort of driven away from zero. If the classifier is sort of correctly predicting them confidently. I think we have some numerics on that, but I also, I guess, didn't put them in. Anyway, so we imagine we're in this sort of setting where with the states that we care about, we actually have like a genuine sort of finite gap between zero and our initial expectation value. And we can then sort of meaningfully ask, like, how much tolerance do we have, like sort of wriggle room? And then just, I guess, using this sort of standard characterization of like the one norm is sort of operationally, like talking about the distinguishability of states. Yeah, we have this upper bound, and then we can just sort of actually just like calculate if you change like the input data a little bit, how does that, change? Well, we can bound how much that can change the expectation values that you calculate. And what we find is that if you do angle encoding, this is kind of extensive. So for like very large systems, changing all the pixels, say, in your image a little bit, this is actually going to change the quantum state sort of quite drastically in terms of the fidelity. But with amplitude encoding, for example, it doesn't. So you can get this sort of simple, like continuity-based bounce. Thanks. Okay, so then for the next result, we introduce this idea of spatial entanglement of an operator, which you can define just through the sort of standard vectorization. So you associate to an operator the choice state, and then once you have a state, you can just talk about like the entanglement with respect to some spatial bipartition, which we call like the local operator entanglement, like the LOE. And the LOE is kind of cool, like it's sort of indicative of various things. So for example, if it grows linearly with time when you Heisenberg evolve an operator, that's sort of the diagnostic of quantum chaos. And this is, an example of us actually seeing that in some just sort of generic models where everything is sort of nice and, well, not nice, but fully expressible. And you see the LOE sort of grows linearly. All right, so we'll come back to that in a second. But the last result, for which we're going to employ the LOE, relates to universal adversarial examples. So the way I was setting it up before, it was kind of like you have a single input state, and then you come up with some perturbation that's going to trick the classifier. But it would be better if you had like a sort of input state independent perturbation that you could add to anything, and it would sort of just, automatically flip all the predictions. So it's, I guess, kind of unclear that such a thing would exist, but yeah, it turns out this is, when you sort of look into this numerically, you can find these sort of perturbations. So then in like the QML context, we sort of model this as the adversary essentially having the power to apply a unitary after the data encoding step that's going to map the states to a different state in a way that's independent of x. And then, okay, I guess it's not so hard if you just sort of like write down the sort of the chain of implications for that. You find that you want the Heisenberg evolved W, which is what the adversary can in effect implement, to anti-commute with the operator that you measure at the end. So if it's, say, like said tensor K, I mean, it's maybe not so hard to think of things that anti-commute with that. But that's not what the adversary actually gets to implement, right? They implement W, and they want its Heisenberg evolved version of it to anti-commute with, say, Z to the K. But W is actually constrained by like the data encoding, right? So if you're doing angle encoding, then this is like just a local operation that the adversary can effectively do, right? Just sort of changing all the pixels or whatever of the image. But so now this is like sort of two contradicting requirements, right? So you have this sort of originally, right, so not necessarily like zero, but low LOE based operator that, say, only has x's and y's on the first k qubits. And then you want to Heisenberg evolve that, backwards evolve that to something that's local. But from like the pictures from a few slides ago, like this is not what happens in the generic circuits. Like the LOE goes up, not down. And then, okay, we can sort of like formalize this a little bit and actually calculate the distance from a given operator to a product operator. And yeah, if the LOE is high, then this distance is large. So the operational, I guess, the operationally meaningful metric is actually like the success fraction of adversarial attacks, not this weird two-norm distance thing. But yeah, we also have just some numerical evidence of that being like really strongly correlated with LOE. Yeah, so I guess that's basically the end. If you haven't seen it before, this adversarial vulnerability stuff is kind of wild. Like you would expect, like it's sort of easy to be convinced that these neural nets are like somehow like really understanding what's going on. So especially if you remember like the first picture, like it looks like it knows like what the people are, what the road is, this sort of thing. But yeah, I don't know, it's very suspicious. Anyway, then we have some numerical evidence about quantum classifiers sort of resisting attacks that are transferred from classical networks. We have some little continuity-based guarantees and some results about the LOE protecting us in the case of universal examples. And then, yeah, this last result is maybe a bit suspicious because, so for example, these sort of fully expressible circuits actually, I mean, you can't train them, right? So, and the LOE is also, you can actually bound it. So if you had a trainable like model with, say, a small DLA, you would also have small LOE. So it might also be sort of like trainability and simulability being the same thing. Yeah, we think it might also be the same for robustness. But yeah, anyway, that's the end.
Thanks a lot. Great talk. So one question that I guess that I have, you took a look at the perturbation sensitivity for various types of encodings, but at some level, you actually don't care about the perturbation sensitivity of the state. You rather you care about the decoding of relevant information from the state after the perturbations. So I'm kind of curious, have you tried taking a look at this through the lens of quantum error correction, where you could end up seeing your concept classes as being code spaces and look at what these perturbations might end up meaning there?
No. That's a cool idea though, yeah. But no, we haven't thought of that. Thanks.
Hello, thanks so much. Just a question on the first plot where you disturbed the quantum model also with the same pattern. So just to remind me, like these patterns are constructed for neural networks, so you can't just have any perturbation, right? You have to like understand, or you have to compute them somehow from the weights of your neural network, or I don't know if you mentioned that, sorry.
Yeah, exactly. So you just take like the neural network as like just some fixed object, and you do just like gradient like ascent on like the actual input to try and maximize the loss function.
Okay, I mean, the conclusion was totally safe. It just says like in the quantum model something else is going on, so that I totally agree. Yeah, nice. Thanks.
Oh yeah, sorry. So just super quickly, so you could also do this like targeting like a quantum model, right? You just treat it as like a black box and like optimize the input, and yeah, that would completely break it too. Yeah.
Yes, so related actually to this graph as well. So you're comparing convolutional nets and rest nets, etc., where you input the whole image, right? With the VQCs. What was the input of the VQC? How did you encode the images? Did you do any PCA dimensionality reduction or anything?
So these little MNIST guys, they're only like 28 by 28, so you can like amplitude encode it into like 10 qubits.
Okay.
Because 28 squared is less than 1024.
Okay. Thank you.
All right, last question.
Nice talk. Do you think that there are other perturbations that the quantum can be not as robust as the classical classifiers? Did you have explored that? Because this kind of perturbation, the classical machine learning community has come up with this perturbation that affect the classical, but can we find something that is similar for the quantum classifiers?
Yeah, absolutely. So the perturbations do exist for like the quantum models too, but it's a question of like how do you actually like find them? So if the quantum model is like somebody else's, it's like some black box thing that you can't sort of access. Yeah, I'm not sure how you would necessarily find it. It's like the way you do it classically is you just attack your own network and then transfer it. But if that's not working, yeah, that's the idea.
All right, let's thank Max.